Welcome back. When you hear the word concrete, what's the first thought that comes to your mind? If you're thinking of a sidewalk or a parking garage or one of these ugly gray blocks, well, you're not alone. Concrete is the most commonly used construction material, so many of its uses tend to be, well, common, mundane. But in today's lecture, we'll have an opportunity to see the most underappreciated of all construction materials in new and exciting ways. By the time we're done, I hope the word concrete will conjure up some very different images. Like these. Frank Lloyd Wright's Falling Water, named the all-time best work of American architecture by the American Institute of Architects. This building's characteristic feature, those cantilevered balconies, are reinforced concrete. Robert Maillart's stunning Zalgan-Itobel Bridge. Contrary to its distinctly modern appearance, this beautiful concrete structure is over 80 years old. Pier Nervi's Palazzo dello Sport in Rome, its most impressive feature, a beautiful ribbed dome made entirely of reinforced concrete. And Sydney's most famous structure, the Opera House, with its distinctive curved shell roofs, all reinforced concrete. This even more astonishing roof at the City of Arts and Sciences in Valencia, Spain, an impossibly thin concrete shell. And finally, the world's tallest building, the Burj Khalifa in Dubai, a towering monument to modern reinforced concrete technology. As you think about this incredible range of structural configurations, I hope you'll begin to think about this common material in an uncommon way. And then next time someone uses the word concrete, I hope the first thought that will come to mind is versatility. We'll be visiting each of these great concrete structures and many more over the next 2 lectures. Today we'll look at a wide variety of beautiful concrete buildings and bridges that are nonetheless conventional, because they're composed of the basic structural element types we've discussed thus far in the course. The versatility of concrete derives from the way it's made. Remember this? It's the concrete capital that I made back in Lecture 4. I made it by mixing Portland cement powder with sand, gravel, and water to create a semi-liquid that could be poured into temporary forms of virtually any shape, to create a rock-like solid of virtually any shape. The construction of full-scale concrete structures works exactly the same way, except the batches of concrete are just a bit larger. As we saw in our lecture on engineering materials, the story of modern concrete technology really begins with the invention of Portland cement by Joseph Aspdin in 1824. As a manufactured product, Portland cement could be produced in much larger quantities and with much better quality control than that volcanic ash called pozzolana that had been used by the ancient Romans. And so, soon after Portland cement became available, concrete became popular as a replacement for stone in the foundations of buildings and bridges. By the 1850s, engineers were starting to experiment with concrete arch bridges and aqueducts, a fairly logical structural application given the material's high strength and compression. But the full potential of concrete as a structural material wouldn't be realized until its most important limitation, its inherent weakness and tension, was overcome. The decisive technological breakthrough came from an unlikely source, a French gardener named Joseph Monnier. In 1867, Monnier developed a system for making large flower pots using concrete reinforced with iron rods. The success of these products led Monnier to realize that iron reinforced concrete might actually be useful in the construction industry. And so this gardener turned engineer conducted a series of amazingly well-conceived experiments on concrete structural elements. And based on these experiments, he worked out a system for placing reinforcement in the regions of a structural member where tension occurs. And that is the most fundamental characteristic of modern reinforced concrete. Now, in our lecture on beams, we learned that a flexural element experiences compression on top and tension on the bottom. But if we make a beam out of plain unreinforced concrete and we subject it to flexural loading, it will crack and ultimately collapse. A reinforced concrete beam is designed to rectify that problem. What we do is to cast metal bars, either iron or steel, into the beam on the lower surface, that is the portion of the beam that undergoes tension. Now, I've created a little bit of a model here just to serve as a demonstration, and I can't cast bars into this beam, so what I've done is to simply stretch 3 steel wires, very slender steel wires, across the bottom of the beam. It's otherwise identical to the one that I just showed you a moment ago, but now because of these wires, when I subject this beam to flexural loading, you'll notice that it is significantly stiffer. It carries loads significantly more effectively because those steel wires are now carrying the tension that occurs at the lower portion of the beam while the concrete continues to carry the compression in the upper portion. Now, you'll notice in my model that when the beam flexed, the concrete still cracks. And that's not a problem. In fact, the fact that the concrete cracks is actually absolutely essential to the functioning of reinforced concrete. As you recall, when any material is subjected to tension, it elongates, and steel is certainly no exception. Remember the stress-strain curve of steel. For every amount of additional stress, there's a corresponding amount of strain. With regard to concrete, there's a characteristic strain at which the concrete will crack, and that strain is very small. If we tried to design a reinforced concrete beam so that it wouldn't crack at all, then we would have to use a tremendous amount of steel, and we'd have to design the beam so that the amount of strain that occurred in both the steel and the concrete was extremely small. In doing that, we would be using only a tiny fraction of the steel's capacity. And so in order to use the steel efficiently, we need to give it an opportunity to elongate under load, and when it does that, the concrete will crack. In effect, cracking is good simply because it demonstrates that the full capacity of the steel is being used in carrying flexural loads in the beam. And don't worry, this cracking is controlled because the concrete remains firmly bonded to the steel, and therefore the cracks will only open up as far as is necessary for the full strength of the steel to be utilized in the reinforced concrete beam. Steel reinforcement can also be used to strengthen concrete in compression. Typically, though, compression reinforcement is not required to the same extent as tension reinforcement, so we usually don't have as much of it in the compression region of a beam as we see in the tension region. Whether in tension or compression, the steel bars can only carry load if they're firmly bonded to the concrete. Now, in the early years of reinforced concrete construction, the bars were actually square iron rods that, prior to the installation in the reinforced concrete element, were twisted into a spiral like this, so that those spiral-shaped ridges formed by the corners of the bar would grip the concrete more effectively. Over time, that technology was replaced, and now modern structures use circular steel or iron rods that look just like this, where we now have raised ridges on the bar itself that provide that same mechanical bond between the steel and the concrete. Reinforcing bars are normally pre-assembled into a self-contained cage like this one here, and then that cage is placed inside the forms, and then the concrete is poured in and vibrated to consolidate it around those reinforcing bars. Once the concrete is cured, those mechanical ridges on the steel reinforcing bar that I just showed you form that strong mechanical linkage between the steel bar and the concrete so that the member as a whole can carry load as an integrated unit. Now that we've seen how reinforced concrete structural elements work, let's see how this new technology influenced the design of great structures in the century and a half after Joseph Monnier invented it. In Europe and the United States, several entrepreneurs capitalized on Monnier's work by developing comprehensive systems for reinforced concrete buildings. The most successful of these was François Hennebique, who patented his system in France in 1892. The Hennebique system was revolutionary in that it provided fully integrated structural systems, floor slabs, beams, columns, foundations, exterior facades, and roofs, all in reinforced concrete. This 3D model shows a typical example of the interior structural frame of a Hennebique building. Unlike an iron or steel structure, the columns, beams, and floor slabs are not fabricated as separate structural elements and then assembled. Rather, they're all cast together as a single monolithic unit. And if we cut away the concrete in this representation here, we'll see an arrangement of iron reinforcing bars that's essentially indistinguishable from modern reinforced concrete construction. Hennebique built few structures himself. Rather, he licensed this technology to contractors, and then he very closely managed the quality of their materials and construction methods. His system was enormously successful. By 1899, over 3,000 Hennebique structures had been built worldwide. By 1909, that number had grown to around 20,000. Here's a typical example. The Royal Liver Building in Liverpool, England. This grand structure was completed in 1911 and remains one of Liverpool's most famous structures today. It is entirely reinforced concrete, inside and out, a fine example of the advanced state-of-the-art just 2 decades after Hennebique developed the system. In the U.S., the development of reinforced concrete was pioneered almost exclusively by an English immigrant named Ernest Ransome, who developed a similar system very similar to Hennebique's in the late 1800s. In 1903, Ransome's system was used in the world's first reinforced concrete skyscraper, the Ingalls Building in Cincinnati. At 16 stories, it was only about half as tall as the tallest steel frame building at that time. Nonetheless, it was a groundbreaking structure. The Ingalls Building used integrated beams, slabs, and columns reinforced with twisted iron bars, just like the simulation I showed you earlier. The exterior walls are all solid concrete, though they are faced with marble on the first 3 stories, brick on the next 11, and then terracotta on the top, following the convention of the first Chicago school, as we saw last lecture. Given that the tallest concrete building constructed previously was only 6 stories high, the Ingalls Building was widely viewed as a very high-risk enterprise. Because of official skepticism, it took 2 years to get the building permit approved. And when construction was finally completed and the formwork was removed, one reporter stayed on site all night so that he'd be an eyewitness to the building's collapse. Needless to say, the Ingalls Building didn't collapse, and it remains in use today. And in fact, it is a national historic civil engineering landmark. Although the Ingalls Building was a revolutionary structure from an engineering perspective, it was architecturally conventional, even in its use of the masonry facade that follows Louis Sullivan's tripartite organization of the first Chicago school. But during this period, other architects and engineers were experimenting with new forms that were uniquely tailored to the versatility of concrete. A wonderful example is the Church of Saint-Jean de Montmartre in Paris, one of the world's first non-commercial reinforced concrete buildings. This is a uniquely concrete structure. The slender arches and vaults of that Art Nouveau interior simply couldn't have been built with traditional masonry. The church was under construction from 1894 to 1904, but it didn't really take 10 years to build. Once again, the problem was skepticism over the safety of this new building material, reinforced concrete. A lawsuit delayed construction by several years in this case. And again, the critics were wrong, as the building continues to serve quite effectively as a parish church, even today. More than any other early 20th century structure, the Zalganatobel Bridge in the Swiss Alps reflects the unique qualities of reinforced concrete. It was designed by Robert Maillart, whose bridges are renowned for their beauty and economy. The Zalganatobel Bridge was the product of Maillart's strong technical know-how combined with 3 decades of careful experimentation and observation of concrete structures. Early in his career, Maillart designed several conventional-looking arches made of reinforced concrete, but faced with stone to present a traditional external appearance. But in 1901, Maillart broke with tradition in his Zuoz Bridge, where he used a very thin concrete arch rib, a flat deck, and two spandrel walls to form the world's first hollow concrete box girder. Recognizing that he had, in fact, broken with tradition on this bridge, Maillart didn't add stone facing to the exterior. This would indeed be a uniquely concrete structure. 2 years later, Maillart learned that the spandrel walls of his Zuoz Bridge had experienced significant longitudinal cracking. What most engineers would have regarded as a failure, Maillart saw as an opportunity. After a careful analysis, he recognized that those cracks in the spandrels didn't affect the structural integrity of the bridge. And indeed, they showed that the spandrels weren't really part of the main load path. So he reasoned that he could simply remove most of the material in the spandrels in future designs. That insight led to the extraordinary form of the Zaganatoble Bridge. The structural system of this bridge is a three-hinged arch, shown here in schematic form. The three hinges accommodate thermal expansion and contraction of the arch, as well as the concrete's tendency to shrink as it cures. The unusual shape of the arch segments is directly related to structural load carrying. Because this arch has a relatively short span, 292 feet, its live loading is relatively large in comparison with its dead load. Dead load, of course, is uniformly applied, so it only causes compression in the arch. But because live load can be applied anywhere along the length of the bridge, it also causes flexure or bending in the arch. And so, in the Zaganatoble Bridge, each arch segment must be able to carry load as both a compression member and a beam. And so the profile of each segment, thick in the middle and thin out at the hinges, reflects these two load-carrying modes quite well. The concept is actually essentially the same as Eiffel's brilliant crescent arch on the Garabit Viaduct that we saw some lectures ago. But here, the concept is implemented in an entirely new way, in an entirely new structural material, with two crescents now hinged in the center. It's important to note that the contract to design and build the Zaganatoble Bridge was based on a competition in which the sole selection criterion was low cost. There were 19 entries, and Maillart won, not because he had designed one of the world's most beautiful bridges, though he had, but because this bridge was cheaper than the other 18 entries. Now, this is not to say that Maillart didn't care about aesthetics, but his writing suggests that his aesthetic goal wasn't beauty per se, but rather what he called sincerity of form, a physical configuration that communicates how it carries load. As Maillart demonstrated, a sincere form is also often an economical one. Robert Maillart's structures have been lauded, not only in the world of engineering, but also in the world of art. In 1947, his entire portfolio of structural designs was featured in a one-man show at New York's Museum of Modern Art. And speaking of artistic achievement, we now turn to Frank Lloyd Wright's Fallingwater House. Built from 1934 to 1937 and widely regarded as one of America's greatest works of architecture. The most prominent features of Wright's design are the reinforced concrete cantilever balconies that project out from the building in three directions. And though these cantilevers were intended to evoke nearby rock formations, Wright didn't try to dress them up with stone facing. Like Robert Maillart, he achieved sincerity of form by leaving the concrete surfaces exposed. Unfortunately, Wright was much less competent as an engineer than he was as an architect. His design for the cantilevers used far too little steel reinforcement. The building contractor and a consulting engineer had both recommended more steel, but Wright rejected them both. Ego triumphed over engineering judgment, and the cantilevers began to sag almost immediately after the formwork was removed in 1937. Over time, the deflections grew to 7 inches over a span of just 15 feet. In 2002, the building's caretakers initiated an emergency structural repair after an engineering consultant's analysis indicated that the cantilevers were on the verge of collapse. Here's how that repair was done. This beam represents one of the supporting beams in Frank Lloyd Wright's structure for the cantilevers at Fallingwater. The beams themselves were actually located below the floor structure of the cantilever balconies, so they're not visible when you're actually on the balconies, but obviously they're the critical structural elements that hold the cantilevers up. In their original configuration, the cantilever beams were undergoing extremely large deflections and were on the verge of collapse. What the consulting engineers who did the repair did was to take high-strength steel cables, lay them along the top surface of the beam, as you see here, and then anchor them out at the tip of the cantilever. Once they were anchored, those cables were then attached to powerful hydraulic jacks, which were mounted back at the base of the cantilevers. The jacks were then used to pull those steel cables very tightly in tension in order to raise the cantilevers back up, and then the cables were anchored at their bases permanently so that the cantilevers would not only have their excessive deflections removed, the excessive cracking removed, but also be significantly strengthened so that the threat to the structural integrity of the elements was removed. This process of adding steel and then pulling it tightly in tension in order to strengthen concrete is called post-tensioning. And it isn't just a technique for repairing failing cantilevers. It's now used extensively in all sorts of bridge and building structures. Here's how post-tensioning works. This model represents a typical modern type of bridge structure called a segmental post-tensioned concrete bridge. The bridge itself is composed of a series of segments. Each one of these is precast concrete, which means that it's made in a factory or a manufacturing facility somewhere off of the project site and then shipped to the site on a truck or on a barge. This, as you can see, is the segment of a hollow reinforced concrete box girder, and that extension on the top really just represents the future deck of the bridge, extending out over either side of the box. The bridge then, in this case, will be made of 5 individual segments, but somehow we have to figure out a way to hold the segments together. And that, of course, is the job of the post-tensioning. For the sake of my model, we're going to represent that high-strength steel cable, which is called a tendon, with this piece of rubber tubing. And the way the post-tensioning process works is that first we have to thread it through the individual segment of the bridge, anchor it at one end, so I'm anchoring it out here on the far side. We then pass that steel tendon through the next segment, and we can now bring those 2 segments together. We'll pass the segment through the next, and we'll pass the tendon through the next segment, and again bring the additional segment into contact with our growing bridge. We then pass it through the next segment, bring it together, and finally the tendon is now passed entirely through the structure. At this point, we just have a slack tendon lying inside of a series of concrete segments. We need to add the force that's going to cause those segments to remain together, not only to be able to carry the self-weight of the beam, but also to be able to carry all those externally applied loads once the bridge is in service. To do that, we're going to take that huge, powerful hydraulic jack. We're going to mount it out here on the far side of our bridge. We're going to connect it to the steel tendon, and we're going to apply a tremendous tension force to that tendon, stretching it significantly. And then once the tendon is fully tensioned, we anchor it out here at the far end, cut off the excess tendon material, and we now have a bridge that's capable of carrying its own weight. We can now take it to our bridge site, set it up on top of the abutments, and we have a segmental, post-tensioned concrete bridge ready to be put into service. The tendons, which are stretched with enormous tension to pull the entire bridge together, have the effect of reducing or eliminating all of the tension in the lower portion of this bridge. And the positive effect of that post-tensioning process is both to reduce cracking in the concrete and to reduce the amount of deflection that the bridge undergoes when it's subjected to load. This is the essence of post-tensioned segmental bridge construction. Of course, real bridges can't be built on the ground and then lifted onto the supports in one unit, as I did in my demonstration. Rather, individual segments have to be post-tensioned into place on the existing structure, one at a time. The first bridge in the U.S. to use this technique was the 1,200-foot Lynn Cove Viaduct, which carries the Blue Ridge Parkway around Grandfather Mountain in North Carolina. This area is extremely environmentally sensitive, and segmental construction proved to be well suited to the project's principal goal of minimizing environmental impact. Environmental impact was minimized first by elevating the parkway above Grandfather Mountain. Building a highway directly on the mountainside would have required extensive excavation. By using segmental construction, the bridge could be built almost entirely from above, so that no access roads at all would need to be cut through the forest. The only work done at ground level on this bridge was the construction of 7 concrete piers that would ultimately support the various spans of the bridge. The bridge itself is composed of 153 precast concrete segments, just like the ones I used in my demonstration, except each of those segments weighs 50 tons. Each segment was then transported to the site on the Blue Ridge Parkway. And remember, that's the road that's ultimately going to cross the bridge. Each segment was then lifted into position by a special crane that was mounted out on the partially completed span. The segment was then post-tensioned back onto the existing structure. Those steel tendons were threaded through the segment, attached to jacks, and then tensioned in order to pull the segment into place, forming a cantilever. The crane was then displaced forward out onto that newly installed segment, and then the process was repeated again and again and again until the bridge was complete. Using this process, the construction crews rarely set foot on the ground beneath the bridge. The Lynn Cove Viaduct was opened in 1983 and almost immediately garnered several prestigious awards for both engineering achievement and environmental sensitivity. Its engineer, Gene Figg, went on to design many of America's most beautiful bridges, including the cable-stayed Sunshine Skyway Bridge across Tampa Bay in Florida, a structure we've looked at several times thus far in the course, and the more recent Natchez Trace Parkway Bridge. Note the incredible sweep of that beautiful parabolic arch, which is itself a segmental box girder. And that brings us to the most dramatic demonstration of concrete's versatility, its new role as the material of choice for the world's tallest buildings. In 1998, the Petronas Towers in Malaysia became the first concrete structure to claim the title World's Tallest Building. In 2004, Petronas was surpassed by a steel skyscraper, Taipei 101 in Taiwan. But then again, in 2009, the reinforced concrete Burj Khalifa in Dubai reclaimed the title. It seems that another great skyscraper race is underway. The Burj Khalifa represents a revolutionary new generation of skyscraper technology. Constructed primarily of high-strength reinforced concrete, its structural system is fundamentally different from that of any previous tall building. As this 3D model shows, the overall form of the building consists of a hexagonal core with 3 wings radiating out from the core to form a Y shape. This form is a direct reflection of the structural system, which is called a buttressed core. That hexagonal core is a concrete tube that encloses all of the building's elevator shafts and stairwells. In addition to carrying a portion of the tower's tremendous self-weight and occupancy loads, the core also stiffens the tower against torsion. Indeed, it performs this function in exactly the same way that that box girder on the Severn suspension bridge does. Now, as you probably guessed, those 3 outer wings are the buttresses of the buttressed core system. As structural elements, they work just like the buttresses that were used in medieval cathedrals to prevent the walls from overturning due to lateral loads. In a cathedral, the lateral load is the thrust of the arches. In a skyscraper, the lateral load is the wind pressure. But those three wings are also the building's occupied spaces, consisting mostly of hotel rooms and private residences. How do they hold up the world's tallest building while they're also enclosing roughly 5 million square feet of usable space? To answer that question, let's look at the lower story of the Burj Khalifa. Here's that hexagonal core, and the principal structural elements of each buttress are here. Two reinforced concrete walls that also double as corridors of the occupied space. And at their outer end, a heavier wall that the building structural engineer calls a hammerhead wall. This structure is actually designed to work just like an I-shaped beam, which happens to be turned vertically. The corridor walls are the web of the beam, and that hammerhead is a representation of the flange of the beam. The most fundamental level, the only difference between this system and an I-shaped beam is that the Burj Khalifa extends outward in 3 directions instead of 2 to provide appropriate lateral load carrying capacity all the way around in all directions. This photo of the building under construction clearly shows that hammerhead wall right here. One other important aspect of this structural system is that the spire on the very top is actually a steel truss, extending some 600 feet above the highest concrete elements on the 156th floor. And here you can see that truss, which can't help but remind us of Gustave Eiffel's great tower in Paris. Yes, there is some irony here. The element that allowed a concrete building to become the world's tallest is, well, steel. So what we've seen is that the structural system of the Burj Khalifa consists of a series of medieval buttresses made of concrete, but configured like steel I-beams, surmounted by a modernized version of the Eiffel Tower. And so we see that sometimes revolutionary engineering innovations are actually just old technologies applied in new ways, using new materials. During this lecture, we've seen the many faces of reinforced concrete. But concrete's most unique characteristic is its versatility of form, a sculptural quality that allows engineers and architects to devise forms that are both beautiful and extraordinarily efficient in load carrying. And if you think structures like the Zalganatobo Bridge demonstrate versatility of form, well, the best is yet to come. Next lecture, we'll turn to a special category of structures that carry load in a fundamentally different way. Thin shell structures that attain both strength and stiffness from their curved shape. Structures that stretch concrete to its structural and sculptural limits. Until then, thank you.